Okay, this is one of the most important things I'm going to teach you all year, so please pay attention. Yesterday we talked about the rate of reactions, and I think we looked at this reaction. Pretend it's drawn just like the one that were in your notes. And we said that 2NO2 yields 2NO plus O2. And at time equals 0, you only have the reactants, and then it turns into products while the products start forming according to the stoichiometry of the reaction. And we determined that the rate changes as the reaction proceeds because of the effect of an equilibrium. That means that at some time this starts building up and it starts the backward reaction here, which was all kind of confusing. So today we're going to talk about something called the rate law. What I want you to get out of this is that the rate law is an equation, a mathematical equation, that relates the true rate of the reaction to the concentrations of just the reactants raised to a power, raised to an exponent. And the reason why we use the rate law expression and why anyone gives a hooty patootie about it is not so much 1 and 2, but 2 and 3. You've been lied to for all of your chemical career.
What?
Yeah, yeah.
I'm so surprised.
Turns out that most reactions don't occur, like look at this reaction, A plus B yields C plus D, doesn't happen in this one fell swoop. It happens in a series of steps, and the series of steps is called the mechanism of a reaction. The series of steps, if you added all the steps up together, would give you this reaction. But it isn't just take some A and take some B and it bippity-boppity in one step goes to C and D. This mechanism of a reaction is never exactly known. People take really good guesses, and I guess the really good guess would be as close as you can get. That would be very interesting to know some of the intermediates, some of the stuff that you're making as you're getting from A to B before it gets to C to D. And people want to know that. Now the other thing that is useful about the rate law expression is that equation that we're talking about. It's helpful in classifying the reaction into various orders. I'll talk more about the order in a minute, but I will say this. If the order of the reaction is 1, that means if you double the concentration of the reactants, the rate, or how fast the reaction goes, also doubles. If the rate of reaction is 2, if you double the reactants, the reaction itself, the rate of the reaction goes 4 times as fast. If you have an overall order that's 0, that means changing the concentration of the reactants has no effect on how fast the reaction goes. This would be highly useful if you were an industrial chemist trying to get something made in a hurry. So here we go. Now, the rate law expression, you know that equation, ignores the product to simplify matters. Why does it ignore the products? Because then you have this thing going on. So if we use the rate law expression, that equation, at the moment the reaction starts, we can ignore the products because there aren't any. So our rate law expression, our equation, is called the rate law of initial method. That means right here on our equation. So we're allowed to forget the products. All right. Now, there are 2 types of rate laws. This is the first one that we're going to pay attention to. Let's start right off the bat and not confuse ourselves. This is the differential rate law, and it shows you the relationship between the concentration of the reactants and the rate of the reaction. In other words, if I change the concentration of my reactants, what happens to the rate of the reaction? Okay. But how much is the question? So for this general reaction, A plus B yields C plus D, the rate law has this general form. The initial rate, it is equal to K, which is a constant, times the concentration of A, okay, remember the brackets mean concentration, and for 99% of the time, that concentration will be in terms of molarity. The concentration of A raised to some exponent times the concentration of B raised to some exponent. Here, do yourself a favor and forestall a lot of grief. Write yourself a note. The reactants are multiplied.
Is that the ionized reactants? Or what
No,
is
it has nothing to do with ionization, just the reactants.
So
of the
what if
rate.
there's only one?
It has nothing to do with the coefficients either. Hang on for just a second, okay? Here we go. Now, this M and N are not the coefficients, These exponents can only be determined experimentally. The value of K, the constant, can only be found experimentally. K does not depend on the concentration of the reaction. The only time this constant varies is if temperature changes. Now, this reaction order that I'm talking about are the coefficients. You can talk about it a couple of different ways. Let's just look at A in isolation. When I say the order of A, that means the number M, the exponent on the concentration of A in that rate law. How do I find the order?
Experiment.
Thank you. Experimentally. You can only find this exponent in experimentally. Is it the coefficient?
No.
No, can't fool you. Okay.
Try it.
All right. The overall order of B is also an experimentally determined value.
So I mean, they're gonna give it to us in the problem.
No, you're going to look at experiments and figure it out. You'll love it. Okay, stop moaning. It's not even that hard, you baby heads. The overall order refers to the sum of the exponents. Here, look. Here is a reaction 2H2 plus O2 yield 2H2O. The overall order, the overall rate law, the general form of it is rate is equal, the experimentally determined rate law expression is rate is equal to K, H2 times O2. Hey, remember about chemists? They're really lazy. They never write the number. If there is no order written above the brackets, you're going to assume it is 1. So the overall order for this reaction would be 1 plus 1 or
2.
Thank you. For this reaction, it has been determined experimentally that the rate law expression is rate is equal to K times the concentration of HCl times the concentration of NH3 raised to the second power. The overall order of that is 1 plus 2 or
3.
There you go.
Minus the NH3O2.
It was experimentally determined that doubling the concentration of NH3 would quadruple the rate.
Okay.
Okay. Now, here we go again. If the order of a reaction is 1, whatever the reactants do, the rate does. If you double the reactant, the rate is doubled. If the overall order of the reaction is 2, you double the reactants, you quadruple the rate. Any number raised to the 0 power is equal to 1. That means in a 0 order reaction, the concentration doesn't matter. All right, here is a really tricky bit that I need you to know. This rate law constant, K, stays the same except when temperature changes. The AP folks and I are going to use a code that I would like to clue you in on. K, the rate law constant, that changes when?
When temperature changes.
Thank you very much. Has units to it. These units will tell you the overall order of the reactant that it's associated with. Did you hear that?
No.
The unit of K can tell you what the overall order of the reaction is. I need you to be able to decipher this code. The code breaker for this is right here. The units on the rate law constant follow this. I'll explain it in just a second in more depth.
That makes sense.
All right. I'm going to give you problems, and the AP exam is going to give you a problem where they give you just the value of K, the rate law constant, and the unit associated with it. From that, you're going to have to go backwards and write a rate law to do that. If you are unable to do that, you're unable to solve the problem at all, and it will be ugly in a really fast way. This is not that difficult. Used to be, you have to memorize, okay, well, a 0 order K a unit is this, a first order K unit is that, a second order is this. Except that I found this little trick. Now, rate, for the most part, is in molarity per unit time, and generally it's seconds. The rate of any reaction is molarity per second. The rate law constant borrows this molarity, and the way to figure out how to use this is this way. For a 0 order unit for the rate law constant, you take molarity, the number 1, and subtract the order. The order is 0. So molarity, 1 minus 0 is
1.
So molarity times the time value that was given in the rate. Generally it's seconds. Seconds to the -1. All right, now here's just a little stop and note this. Remember that molarity is equal to moles over liters. So you may see it written instead of the M, moles per liters, or you may see it as moles times liters to the -1. These are all the same. I want you to always use this because you won't get it wrong. And AP folks are very accustomed to seeing this. Okay, if you have a first order overall reaction, the rate law constants unit follows this. M, 1 minus the order is first. 1 minus 1 is equal to 0. So the molarity drops out of the unit altogether, and all you have is the time value raised to the -1. Okay, that time value raised to the -1 is the same as saying 1/2 seconds. If you have a second order reaction, the unit that goes with the rate law constant would be m1 minus 2, which is the same as m to the -1 times the time value. Are you good there?
Time value to the -1.
Why don't you do some practicing where it says practice?